So in this lecture, I'll talk about the dual of a normed linear or linear space. So X will be a linear space over a certain field, which can be either the real numbers or the complex numbers. And remember that L from X to K is a linear functional well, if it's linear, which means that if for all x and y in X, Lx plus y, it's equal to Lx plus Ly, and for all scalar alpha, L of alpha x is equal to alpha Lx. And I will start with a definition. So I'll say that a linear functional L is continuous if, well, for all sequence xn converging to x, then L xn converge to L of x. So here I am assuming that x has a norm, so it has a topology, and I will say that this linear functional is continuous if for any sequence converging sequence, then L of xn as a sequence of scalars converge to L of x. And the second definition, I'll say that L, a linear functional, so let me write with capital letters for linear functional, is bounded. So now I'm defining bounded if there exists a constant C0 such that a finite constant such that L of x is less or equal than C0 times the norm of x for all x in X. So it will be, a linear function will be said to be bounded if there exist these finite constants for which this inequality holds for all points. And let's say my first observation, proposition, say that a linear functional L is bounded if and only if it's continuous. If and only if it is continuous. So there is one claim which is very simple to prove, which is, well, assume that this linear functional L, so L, remember, it's defined on over all space on K. So assume that it's bounded. So assume that there exists a constant for which this holds. Let me prove that it's continuous. To prove that it's continuous, consider a sequence xn converging to x. This means that, well, the norm of the difference xn minus x converge to 0. But then let me show that L, it's continuous. We have to prove that L of xn converge to L of x. Let me take the absolute value of the difference. By linearity, this is equal to the absolute value of Lxn minus x. By the fact that it's bounded, this is bounded by a constant C0, the norm of xn minus x. And this converges to 0 because I'm assuming that that xn converge to x, which means that the norm of the difference converges to 0. So we proved that if you have a linear functional which is bounded, it is continuous. So now let me show the converse statement. So let me assume now that L is continuous, and let me prove that this implies that L is bounded. Well, if I will prove by contraposition, so let's assume that L is not bounded. So I'm saying that if this is false, then this is false. So let's assume that L is not bounded, which means that for all n, there exists xn such that, well, so I'm assuming that it's not bounded. That means that this is not true, which means that for all n, I can find xn for which that L of xn, it's larger than n times the norm of xn. So we have a sequence, xn. Let me define a new sequence, yn, which is xn divided by the norm of xn, and this divided by square root of n. So this is a new sequence. Yn, the norm of yn, it's equal to the norm of this element, but this is 1 divided by square root of n times the norm of this element, and this is 1. So the norm of yn, it's 1 divided by square root of n. And on the other hand, L of yn, well, this is equal to, well, let me write it, the absolute value of L of this expression. So I have 1 over square root of n, which goes away, the absolute value of xn, which goes away, and then L of xn, but L of xn in absolute value, it's bounded below by n times the norm of xn. So the norm of xn cancel with norm of xn, n cancel with square root of n, and this is equal to square root of n. So here I have a sequence yn. Yn, it's converging to 0 because its norm it's equal to 1 over square root of n. So yn is going to 0, but L of yn is not going to L of 0, which is 0, because L of yn it's bounded below by square root of n. So I obtained a sequence yn, which is converging to 0, but L of yn it's not converging to L of 0, and therefore L is not continuous. So we proved that if L is not bounded, then it's not continuous, which shows that if L is continuous, then it's bounded, and this completes the proof of this first proposition. So definition, that's a definition of a dual, the dual of a normed linear space X. I will represent this space by X prime. So X prime, it's the dual of this normed linear space X, and it's the set of all L which are L, it's a linear functional, which is continuous. So this is the space, the dual space of X. So the class or the set of all continuous, and we have seen that this is the same as bounded linear functionals. X prime, it's clearly a linear space. Right? If you have two linear functionals which are continuous, the sum, it's a new linear functional which is continuous. And if you multiply a continuous linear functional by a scalar, you get a new continuous linear functional. So it's a linear space. And let me define a norm. So I'll define a norm of a linear functional as follows. Well, that will be given by the supremum over all x different from 0 of L of x divided by the norm of x. I can divide by the norm of x because I'm assuming x different from 0. But you see, I can put inside the norm inside this absolute value. So this is equal also to the supremum for x different from 0 of L of x divided by the norm of x. And you see that here I have an element whose norm is equal to 1. So this is also equal to the supremum over all x such that the norm of x is equal to 1 of L of x. And you immediately get from this definition that, well, L of x, it's bounded by the norm of L times the norm of x. So this is true for all x. From this definition, this is true for all x different from 0. But if I get x equal to 0, this inequality also holds. So this inequality holds for all x in x. And this is a very simple consequence of the definition of the norm. So here's the definition. Now I leave it to you as an exercise to show that this definition, so this equation, defines a norm in the dual space. So I leave it to you to check that all three properties of a norm are satisfied, and therefore that this equation, one of these equations, defines a norm in the dual space. So I wrote on this side the definition, and I will now prove a very simple facts about the dual space. So the first proposition relies on the definition. So if I have L, a bounded linear function, an element of the dual space, I will define the null space of this linear functional as the set of all points z in X such that L of z is equal to 0. And I will call that the null space of L. Right, so the null space of a bounded linear functional is simply the set of all points which are set to 0 by that linear functional. And what I claim is that N is a closed linear space, subspace, and also that its codimension is equal to 1. So assume that L is different from 0. Now, if L is different from 0, what I'm claiming is that the codimension of this null space is 1. That means the following. There exists a point X in X such that all Y in X, for all Y in X, there exists alpha in the scalar alpha, and there exists an element n in my null space n, such that y is equal to alpha times x plus n. So you see, this means that any element of x can be written as, well, a scalar multiplying a multiple, if you want, if you wish, of x plus an element of the null space. And of course, x will not belong to the null space, so we'll see that actually these two spaces have an intersection which is equal to 0. So let me prove these two statements and then clarify what I just said. So that n is a closed linear space. Well, it's that n is a linear space. It's very easy. You take two elements in the null space, Z1 and Z2, they are sent to 0, so the sum by linearity is also sent to 0. And the same thing if you multiply an element of the null space by a scalar, the scalar times this element will be sent to 0. So N, it's clearly a linear subspace. That it's closed, well, assume that you have Xn converging to X, and that Xn belongs to the null space. Then what I claim is that X also belongs to the null space. And why is that? Well, L, it's a bounded linear functional, therefore it's a continuous linear functional. This means that L of X is the limit in N of L of Xn. But Xn belongs to the null space, so L of Xn it's equal to 0, and this means that L of X it's equal to 0, which means that X belongs to the null space. So this proves that indeed N is a closed linear space. So this proves the first statement. So now I will erase and prove the second statement of this proposition. Now, to prove the second statement, so I'm assuming that L is different from 0. If L is different from 0, this means that there exists an X in X such that L of X is different from 0. So let me fix this X. This is the X which appears in the statement. And now let's take Y. And I want to write Y as alpha X plus an element of the null space. So the question is how to define alpha and n. I have to show that there exists this alpha and this n. Well, let's use the properties we want to match. So if I apply L to both sides of this identity, I use linearity of L and the fact that n belongs to the null space, so that L of n is equal to 0. So this is equal to alpha of Lx. So Lx is different from 0, so I can divide by Lx and get that, well, for that to be true, alpha has to be equal to Ly divided by Lx. So I have a candidate for alpha. Alpha is Ly plus Lx. And therefore, I get from this identity here that n has to be equal to y minus alpha x. So n will be equal to y minus alpha. I just computed it's L of y divided by L of x times x. And let me check that n belongs indeed to the null space. So let's apply L to both sides. L of n, it's equal to L of this expression. But L of this expression, by linearity, it's L of y minus, well, this is a scalar, so I get L of x. Multiplying this scalar, L of x will cancel with L of x. L of y will remain, which will cancel with this L of y. So from this computation, I get that indeed L of n is equal to 0, which means that n belongs to the null space. So whatever y, I can write y as L of y divided by L of x, x plus n, but n is y minus L of y divided by L of x, x. And this second piece is, we have seen, belongs to n, and this first piece, it's a scalar which is multiplying by x. So this proves the statement that, well, we found a point, an element x of our normed linear space, which has the following property: whatever y we pick in x, we can write y as x multiplied by a scalar plus an element of the null space. And what I now claim is that, well, I have here a linear space. So let me call that the linear space maybe Z. So let me call Z the alpha x such that alpha is a scalar. And what I claim is that the intersection of Z with n, it's equal to the element 0. So let's prove this statement. So I have, let's pick an element y, which is in the intersection. So on the one hand, y belongs to z. So y, it's equal to alpha x for some x, for some alpha. On the other hand, y belongs to n. So I know that L of y, it's equal to 0. So from this, I get that 0, it's equal to L of y. L of y, it's equal to alpha Lx. So this is equal to alpha times Lx. But Lx is different from 0. So I get that alpha, it's equal to 0. So, well, y, it's equal to alpha x. But alpha is 0. So this means that y, it's equal to 0. And this is exactly what we wanted to prove, right? We showed that whatever point y I take in the intersection between z and n, the unique element is the origin. Therefore, I have two properties about this space z and the space n. On the one hand, any element of x can be written as the sum of an element in n and an element in z. On the other hand, the unique point in the intersection of these two sets, which are linear sets, is the origin. So I will write these two properties with the following notation. X, it's equal to a direct sum of z and n. So this means that any point in x can be written as a sum of a point in z and a point of n. And moreover, that the intersection of z with n is the origin. And this is exactly what we proved. And we also proved that z is formed by all points in the linear space x, which can be written as a scalar times one point, which means that the dimension of z is 1. So z, it's a one-dimensional space. And therefore, and this is what I mean by codimension of n. So that x can be written this way, and that the dimension of the set z is equal to 1. This is what we just proved. So now, an interesting proposition is that, well, this normed linear space x prime is complete. So we are not assuming that x is complete, and we will prove that, well, whatever x prime is always a complete normed linear space. The proof, it's quite simple. So in order to show that this space is complete, we consider Ln. So this is a sequence which is Cauchy. In x prime. Well, it's a Cauchy sequence. This means that for all epsilon positive, there exists n0 such that if n and m are larger than n0, then the norm of Ln minus Lm is bounded by epsilon. And what we need to prove, we need to show that there exists L in x prime such that Ln converge to L in x prime. So the proof is again in two steps. We first have to construct this linear functional L, show that it belongs to X prime. That means that it's bounded. And then the second step consists in proving that Ln converge to our candidate L. So let's start with the first part of the proof, constructing this linear functional. Well, what I claim is that for all x in X, Ln of X is a Cauchy sequence. And this sequence is a sequence of scalars, so a sequence of points in K, which is a complete field. So if this is a Cauchy sequence, it converges to some point, and that point, that limit, will be our definition of L of X. So let me write down what I just said. First, I claim that this is a Cauchy sequence, so you fix an epsilon positive, where you know that there exists this n0 such that if nm are larger than n0, then this bound holds. Now, Ln of X minus Lm of X, if you remember the bound I proved at the beginning of this lecture, this is bounded by the norm of Ln minus Lm, right? The difference of this is not a limit, this is just Lm. So Ln minus m at x is just the difference of Ln at x minus Lm at x. So this is actually Ln minus Lm at x. And by the bound I proved at the beginning of this lecture, the absolute value of this quantity is bounded by the norm of Ln minus Lm times the norm of x. But the norm of Ln minus Lm by our choice of n0, so this is bounded by epsilon times x. And this proves that indeed this sequence Ln x is Cauchy. So this is a Cauchy sequence. So this implies that Ln x converge to some z in K, or some alpha in K. And this will be the definition of Lx. So I'll define Lx as this limit. So Lx will be the limit in n of Ln x. So it's clear that L is linear. Right, you take Lx plus y, but this is the limit in n of Ln x plus y by definition, but this limit is equal to the limit by linearity of Ln x plus Ln y, and by definition of Lx and Ly, this is Lx plus Ly. So this proves that L of x plus y is equal to Lx plus Ly. In the same way, you can prove that L of alpha x is equal to alpha Lx. So this proves linearity, and the last step consists in showing that, well, Ln is bounded. So we need to prove that, we want to prove that L is bounded, so that L is an element of x prime. So we need to prove the existence of a constant C0 for which L of x is bounded by these constants times the norm of x. But this, by definition, it's the limit of Ln of x. Now, Ln of x, by the same bound I mentioned, this is bounded by the limit sup as n goes to infinity of Ln, the norm of Ln times the norm of x. And now, if you remember, we have here a sequence which is Cauchy, and I proved that any Cauchy sequence is bounded. So this means that there exists a constant C0 such that the norm of Ln is bounded by C0. And therefore, that this is bounded by C0x. And this is exactly what we wanted to prove. So we proved that L, which is defined as the pointwise limit of Lnx, of Ln, right? We proved that for any x, Lnx converge, and we defined L as the pointwise limit, so L of x as the limit of Lnx. We proved that the function defined by this formula is linear, is actually a bounded linear functional, and therefore we have now our candidate L, bounded linear function. And what remains to be done is to prove that Ln converge to L in the norm. So we proved that L defined as L pointwise as Lx as the limit of Lnx, that this formula, well, the limit exists, and this formula defines an element of the dual space. Now I want to prove, in the second step, that Ln converge to L in the norm. So fix epsilon positive. Now, with that fixed epsilon, you know that there exists an n0 for which n and m larger than n0 imply that the norm of Ln minus Lm is bounded by epsilon. Now let me fix an x. So I know that Ln x minus L of x, well, by definition of L, this is the limit as m goes to infinity of Lnx minus Lmx. And each term, by the bound we've used many times, it's bounded by Ln minus Lm times the norm of x. But this means that if I choose n larger than n0, well, for all m, so in this limit, starting from n0, all successive terms are such that this norm is bounded by epsilon. So this limit, it's bounded by epsilon times the norm of x if n is larger than n0. Now, well, you have this bound, and this holds for all x. So we proved that for all x, Lnx minus Lx, the absolute value of this difference, it's bounded by epsilon times x. So if you recall the definition of the norm of Ln minus L, you get from this bound that the norm of Ln minus L, it's bounded by epsilon, provided n it's larger than n0, and this is exactly what you wanted to prove. We just proved that Ln converged to L in the dual space.